Before we begin, allow yourself to get comfortable. You don't need to picture anything perfectly, and you don't need to remember every detail. This is a slow journey, meant to be listened to gently, like a story unfolding at its own pace. Tonight, we're going to explore volcanoes. Volcanoes are often portrayed as symbols of chaos and destruction, yet in reality, they are also creators. They shape landscapes, build islands, enrich soil, and quietly influence the planet beneath our feet. Imagine the Earth itself breathing slowly. Deep below the surface, heat moves gradually, patiently, over timescales far longer than human lives. Volcanoes are simply places where that internal energy finds a gentle path upward. If you enjoy calm, educational journeys like this, feel free to like the video or subscribe, but only if it feels right for you. And if you'd like, you can leave a comment sharing your country, your city, and the time you're listening. Many people find comfort knowing others around the world are resting at the same moment. Now, let's begin softly. The word volcano comes from Vulcan, the Roman god of fire and metalworking. Ancient civilizations often viewed volcanoes as homes of gods or gateways to the underworld. These stories weren't born from fear alone, but from volcanoes reminded people that Earth is alive, dynamic, and powerful in quiet ways. Scientifically, a volcano is an opening in Earth's crust where molten rock, gases, and ash can escape from below. This molten rock is called magma while it is underground, and lava once it reaches the surface. The journey from magma to lava is slow, sometimes taking thousands of years. Most volcanoes are not constantly erupting. In fact, the majority spend long periods in silence. Some volcanoes may only erupt once in tens of thousands of years. During these long resting phases, they appear peaceful, often covered in forests, snow, or farmland. There are three main types of volcanoes based on shape and behavior. Shield volcanoes are wide and gently sloped, formed by flowing lava that spreads easily. Stratovolcanoes, also called composite volcanoes, are taller and steeper, built from layers of lava and ash. Cinder cone volcanoes are smaller, formed from fragments thrown into the air during eruptions. Each type tells a different story about the magma beneath it. Thick, sticky magma tends to trap gases, leading to more explosive eruptions. Thin, fluid magma allows gases to escape gently, resulting in calm lava flows. Neither is better or worse. They are simply different expressions of Earth's interior. Volcanoes are closely linked to tectonic plates. The Earth's surface is divided into massive slabs that move very slowly, often just a few centimeters per year. Where these plates meet, volcanoes frequently form. Along subduction zones, one plate slides beneath another, melting rock that can rise to create volcanoes. Other volcanoes form at rift zones where plates pull apart. Here, magma rises to fill the gap, creating long chains of volcanic activity. Iceland is a famous example where volcanic landscapes, glaciers, and geothermal energy exist side by side. Some volcanoes form far from plate boundaries, above what are called hotspots. These are areas where heat rises from deep within the mantle. As a tectonic plate moves over a hotspot, a chain of volcanoes can form. The Hawaiian Islands were created this way, one after another, over millions of years. Volcanic landscapes are often breathtakingly beautiful. Black sand beaches, towering cones, fertile valleys, and dramatic cliffs are all shaped by volcanic processes. Many luxury travel destinations exist because of volcanoes, drawing visitors who seek natural wonders, cultural history, and quiet adventure. Volcanic soil is among the most fertile on Earth. When lava breaks down over time, it releases minerals that support agriculture. This is why regions near volcanoes often support vineyards, orchards, and dense populations, despite the risks. Throughout history, people have lived near volcanoes not because they ignore danger, but because volcanoes offer resources. Freshwater springs, geothermal energy, minerals, and rich farmland all come from volcanic regions. Even today, countries use geothermal heat for electricity, heating homes in sustainable and efficient ways. Volcanoes also play a role in Earth's atmosphere. Gases released during eruptions have helped shape the air we breathe. In Earth's early history, volcanic activity contributed to the formation of oceans and the development of conditions suitable for life. Large eruptions can temporarily cool the planet by releasing particles that reflect sunlight. These events are rare, but they remind us that geology and climate are deeply connected, even across vast timescales. Despite their power, volcanoes are studied carefully and patiently. Modern technology allows scientists to monitor ground movement, gas emissions, and seismic activity. These tools help communities prepare and respond calmly when activity increases. Yet most of the time, volcanoes simply rest. They stand quietly, blending into landscapes. Their presence felt more through beauty than threat. Snow settles on their slopes. Forests grow. Animals live undisturbed. As you listen, imagine a volcano not as something violent, but as a slow heartbeat of the planet. A reminder that beneath stillness, there is gentle motion. As we continue, imagine drifting deeper, not through water or air, but gently downward into the earth itself. There is no rush here. The planet has been shaping itself for more than 4.5 billion years, and volcanoes are part of that long, patient story. Far below the surface, the earth is layered like a quiet, ancient library. The crust is the thin outer shell we live on. Beneath it lies the mantle, vast and warm, extending thousands of kilometers downward. Even deeper is the core, a place of intense heat and pressure, slowly generating the energy that drives plate movement and volcanic activity. Volcanoes begin their story in the mantle. Here, rock is solid, but not rigid. Over immense spans of time, it behaves almost like thick honey, flowing slowly under heat and pressure. In certain regions, this rock begins to melt, forming magma. This melting does not happen suddenly. It is gradual, influenced by temperature, pressure, and the presence of water. One of the most common ways magma forms is when tectonic plates interact. When one plate sinks beneath another in a subduction zone, water trapped in the descending plate lowers the melting point of surrounding rock. This allows magma to form gently, collecting in pockets far below the surface. Another path to magma formation happens where plates move apart. As they separate, pressure decreases. Even without an increase in temperature, the rock can begin to melt simply because the pressure is lower. This process, known as decompression melting, is responsible for many volcanoes along mid-ocean ridges. Hotspots offer yet another calm explanation. In these regions, heat rises from deeper within the mantle in slow, steady plumes. These plumes are not violent jets, but broad columns of warmth. As they reach higher levels, melting occurs, and magma slowly accumulates. Once magma forms, it does not immediately erupt. In fact, most magma never reaches the surface at all. It may cool underground, forming igneous rock that becomes part of the crust. When magma does move upward, it does so slowly, following cracks and weaknesses in the surrounding rock. As magma rises, gases dissolved within it begin to expand. This is similar to opening a bottle of sparkling water, but on a far grander and much slower scale. The way these gases escape plays a major role in how a volcano behaves. If gases escape easily, eruptions tend to be gentle. Lava flows quietly, spreading across the landscape in glowing rivers that cool into solid rock. These eruptions can last weeks, months, or even years, steadily reshaping the land. If gases become trapped, pressure builds. When release finally occurs, it can be sudden and powerful. Even then, these events are governed by physics and chemistry, not chaos. They follow patterns that scientists study carefully. Over time, repeated eruptions build volcanic structures. Each layer of lava or ash adds to the shape, much like slow brushstrokes in a painting. The final form of a volcano reflects its entire history, the type of magma, the frequency of eruptions, and the environment around it. Volcanoes are not isolated features. They are part of broader systems that include magma chambers, underground conduits, and surface vents. Some volcanoes share magma sources, forming volcanic fields rather than single peaks. Many famous landscapes owe their existence to these quiet processes. Plateaus, mountain ranges, and entire islands began as magma deep below the surface. Tourism, travel, and cultural identity often grow around these places, blending natural beauty with human history. Even beneath the oceans, volcanoes are at work. Most of Earth's volcanic activity happens underwater, unseen and unheard by people. Along mid-ocean ridges, new crust is constantly forming as magma cools beneath the sea. This slow creation helps regulate the size and shape of the ocean basins. Underwater volcanoes also support unique ecosystems. Heated water carries minerals that feed life forms unlike anything found on land. These deep-sea environments remind us that volcanoes are not just destructive forces, but foundations for life and biodiversity. As magma cools, it records information about Earth's magnetic field, helping scientists understand how the planet has changed over time. In this way, volcanic rock becomes a kind of natural archive, preserving chapters of geological history. All of this happens quietly, far beyond human awareness. Long before an eruption ever becomes visible, the Earth has already done most of the work patiently and methodically. As you rest with these thoughts, imagine the planet beneath you, not restless, but steady. Heat moves slowly. Rock flows gently. Change happens on timescales so long they invite calm rather than fear. As we continue, let your attention drift upward again, back toward the surface, where volcanoes reveal their many forms. Just as mountains, rivers, and coastlines vary across the world, volcanoes also appear in different shapes and sizes. Each shape is a quiet record of how lava moved, how gases escaped, and how time patiently sculpted the land. One of the most common and gentle forms is the shield volcano. These volcanoes are wide and low, with slopes so gradual they can be difficult to recognize as volcanoes at all. Their shape resembles a shield resting on the ground, hence the name. Shield volcanoes are built almost entirely from fluid lava that flows easily and travels long distances before cooling. Because the lava is low in silica, it remains runny and calm. Eruptions are often slow and steady, allowing lava to spread thinly over large areas. Over many eruptions, layer upon layer builds outward rather than upward. This is why shield volcanoes can be some of the largest volcanoes on Earth by area, even if they are not especially tall. Mauna Loa in Hawaii is a classic example. From the ocean floor to its summit, it rises higher than Mount Everest does from sea level. Yet, its slopes feel gentle rather than dramatic. Tourism, travel, and scientific research thrive in these regions. As the landscape is accessible and eruptions are usually predictable. Another familiar volcanic form is the stratovolcano, sometimes called a composite volcano. These volcanoes are tall, steep, and often symmetrical, rising prominently above their surroundings. They are built from alternating layers of lava flows, ash, and volcanic debris, each layer representing a different type of eruption. Stratovolcanoes tend to have thicker magma, which traps gases more easily. This leads to a mix of eruption styles. Some eruptions are slow and lava-rich, while others are more explosive, sending ash high into the atmosphere. Over time, this variety creates the layered structure that defines these volcanoes. Many of the world's most famous volcanoes are stratovolcanoes. Mount Fuji in Japan, Mount Rainier in the United States, and Mount Vesuvius in Italy are all examples. These volcanoes often become cultural icons woven into art, history, and national identity. They attract visitors from around the world, supporting local economies through tourism and education. Cinder cone volcanoes offer a simpler, more modest form. These volcanoes are typically small, steep-sided cones built from loose fragments of volcanic rock called cinders. When gas-rich magma erupts explosively, it breaks into pieces that fall back to the ground around the vent, piling up into a cone shape. Cinder cones usually form quickly, sometimes in just a matter of months or years. They often appear in groups, scattered across volcanic fields. Because they are made of loose material, they erode more easily than other volcanoes, gradually blending back into the landscape over time. Lava domes represent another volcanic shape, one defined by patience and resistance. These domes form when very thick lava slowly pushes its way to the surface. Instead of flowing outward, the lava piles up near the vent, creating a rounded, mound-like structure. Lava domes grow slowly, sometimes over decades. Their surfaces are often rough and fractured, reflecting the stiffness of the lava. While their growth can be calm, domes can also collapse, producing fast-moving clouds of hot gas and ash. Even so, these events follow natural processes that scientists monitor carefully. Beyond individual volcanoes, there are volcanic plateaus, vast regions built from repeated lava flows that spread over enormous areas. These plateaus form when lava emerges from long cracks in the Earth's crust, rather than a single central vent. The lava flows evenly, creating flat or gently rolling landscapes. The Deccan Plateau in India and the Columbia River basalt group in North America are examples of this type of volcanism. These regions played significant roles in shaping ecosystems, influencing climate, and providing fertile soil that supports agriculture and settlement today. Underwater volcanoes also take on unique forms. Seamounts are volcanic mountains that rise from the ocean floor, but do not reach the surface. Thousands of seamounts exist across the world's oceans, many still unexplored. They influence ocean currents, provide habitats for marine life, and are studied for their geological and biological significance. When underwater volcanoes grow tall enough to break the surface, they form volcanic islands. Entire island chains, such as Hawaii and parts of the Canary Islands, owe their existence to this slow, steady building process. These islands often become centers of biodiversity, culture, and travel, blending natural beauty with human stories. Calderas are among the most dramatic volcanic features, yet they form quietly over time. A caldera is created when a volcano empties a large portion of its magma chamber during an eruption. Without support, the ground above collapses inward, forming a broad depression. Some calderas fill with water, becoming lakes. Crater Lake in Oregon is a serene example, its deep blue waters reflecting the sky. Other calderas remain dry, serving as reminders of ancient eruptions that reshaped the land long before recorded history. Even volcanic craters, often confused with calderas, tell their own stories. Craters are usually smaller and form around a vent due to explosive activity or erosion. Over time, they may host forests, lakes, or even towns, blending volcanic history into everyday life. The diversity of volcanic shapes reminds us that there is no single way for Earth's energy to express itself. Each form reflects a balance between heat, pressure, chemistry, and time. None are random. All follow physical laws that operate steadily and predictably. As you picture these forms, imagine flying slowly over the planet, watching shield volcanoes spread gently, stratovolcanoes rise sharply, and islands emerge from the sea. Each one adds to Earth's character, shaping landscapes that support ecosystems, cultures, and economies. Now let your thoughts drift gently across the surface of the planet, as if you were watching Earth slowly turn beneath a soft light. Volcanoes do not appear randomly scattered. Instead, they trace subtle patterns, quiet lines that follow the movement of the planet itself. These lines are not visible to the eye, but they are deeply etched into Earth's structure. Most of the world's volcanoes are found along the edges of tectonic plates. These plates are vast sections of Earth's crust that float slowly atop the softer mantle below. Their movement is gradual, often no faster than the growth of a fingernail. Yet over millions of years, this motion reshapes continents, oceans, and climates. One of the most well-known volcanic regions is the Pacific Ring of Fire. This immense horseshoe-shaped zone encircles much of the Pacific Ocean. It stretches from the western coasts of the Americas, up through Alaska, across eastern Asia, and down toward New Zealand. Along this ring, volcanic activity and earthquakes are especially common. The Ring of Fire exists because several tectonic plates meet and interact there. In many places, one plate slides beneath another in a process known as subduction. As the descending plate sinks deeper, it heats up and releases fluids into the surrounding mantle. This lowers the melting point of rock, allowing magma to form and rise toward the surface. These subduction zones give rise to chains of stratovolcanoes, often aligned in graceful arcs parallel to deep ocean trenches. Over time, they create dramatic landscapes marked by mountains, valleys, and fertile soils. Many densely populated regions lie near these volcanoes, benefiting from rich farmland and abundant water, while also learning to coexist with natural risk. Not all volcanoes form at subduction zones. Some appear where tectonic plates pull apart. These areas are called divergent boundaries. As plates move away from each other, pressure on the underlying mantle decreases, allowing magma to rise and fill the gap. This type of volcanism is common along mid-ocean ridges, which form the longest mountain chain on Earth. Most of this chain lies hidden beneath the sea, where new oceanic crust is constantly being created. Lava erupts quietly along cracks in the seafloor, cools quickly in the water, and slowly expands the ocean basins. Iceland offers a rare glimpse of this process above sea level. The island sits atop the mid-Atlantic ridge, where the North American and Eurasian plates are drifting apart. Volcanoes there often produce fluid lava flows, geothermal activity, and landscapes shaped by both fire and ice. Volcanoes can also form away from plate boundaries in places known as hotspots. These regions are fed by columns of unusually hot mantle material rising from deep within the earth. As tectonic plates move over these stationary hotspots, chains of volcanoes develop over time. Hawaii is perhaps the most famous hotspot system. The islands form a line that records millions of years of plate movement. The youngest and most active volcanoes sit above the hotspot today, while older islands gradually erode and sink as they drift away. Hotspot volcanism tends to produce shield volcanoes with broad, gentle slopes. The eruptions are often less explosive, allowing scientists to study them closely. These regions also become important centers for tourism, education, and long-term geological research. In continental regions, hotspots can create massive volcanic features. Yellowstone, in the United States, sits above a powerful hotspot beneath the North American plate. While it is often discussed for its geothermal features, its volcanic history spans millions of years and includes some of the largest eruptions known on land. Beyond these major patterns, smaller volcanic fields dot the planet. These areas may contain dozens or even hundreds of small volcanoes spread across a region. They often form where the crust is thin or fractured, allowing magma to rise through weaknesses in the rock. Africa's East African Rift is one such region. Here, the continent is slowly splitting apart, creating valleys, lakes, and volcanoes. This rift has played a role in shaping ecosystems and may even have influenced early human evolution by altering landscapes and climate patterns. Volcanoes beneath the ocean deserve special attention as well. Submarine volcanoes are far more numerous than those on land, though they are less visible. Their eruptions usually occur quietly, cushioned by water pressure, but they play a vital role in shaping the seafloor and supporting unique marine life. Hydrothermal vents, often found near underwater volcanic activity, release mineral-rich fluids into the ocean. These vents host ecosystems that thrive without sunlight, relying instead on chemical energy. Studying these environments helps scientists understand life's adaptability and even informs the search for life beyond Earth. Volcanic islands often act as stepping stones for life. Over time, plants, animals, and humans reach these islands, adapting to isolated conditions. This leads to unique cultures, languages, and ecosystems, many of which are carefully protected today through conservation and sustainable tourism. The global distribution of volcanoes reflects a balance between creation and renewal. Lava builds new land, ash enriches soil, and geothermal heat provides energy. At the same time, erosion, weather, and plate movement gradually reshape these volcanic landscapes. Understanding where volcanoes are found helps communities prepare and adapt. Modern technology allows scientists to monitor ground movement, gas emissions, and seismic activity. These tools improve safety while deepening our understanding of Earth's inner workings. As your breathing slows, imagine these hidden lines beneath the planet, glowing softly with warmth and motion. They are reminders that Earth is not static, but alive with slow, steady change. As we continue gently onward, allow your thoughts to rise upward, following a column of warm air drifting from a distant volcanic peak. Volcanoes do not only shape the land beneath our feet. At times, they also reach into the sky, quietly influencing weather patterns, climate cycles, and even the course of human history. When a volcano erupts, it releases more than lava. Ash, gases, and fine particles are carried upward, sometimes reaching the highest layers of the atmosphere. The scale of this influence depends on the size and nature of the eruption. Some eruptions are small and local, while others are powerful enough to leave a global fingerprint. One of the most important volcanic gases affecting climate is sulfur dioxide. When released high into the atmosphere, sulfur dioxide reacts with water vapor to form tiny sulfate aerosols. These particles can spread around the globe, reflecting a portion of sunlight back into space. This reflective effect can lead to temporary cooling of Earth's surface. Temperatures may drop slightly for months or even years following a major eruption. While the change is subtle on a daily basis, it can influence growing seasons, rainfall patterns, and ocean temperatures. A well-documented example is the eruption of Mount Pinatubo in the Philippines in 1991. This powerful eruption sent enormous amounts of sulfur dioxide into the stratosphere. Over the following 2 years, global average temperatures cooled by about half a degree Celsius. This event provided scientists with valuable data on how volcanic aerosols interact with climate systems. Earlier in history, the 1815 eruption of Mount Tambora in Indonesia had even more dramatic consequences. The following year became known as the year without a summer. Crops failed across parts of Europe and North America, leading to food shortages and social unrest. Despite these disruptions, volcanic cooling is temporary. Over time, aerosols settle out of the atmosphere and climate systems gradually return to balance. Unlike greenhouse gases, volcanic emissions do not accumulate for centuries. Instead, they offer brief glimpses into the sensitivity of Earth's climate. Volcanoes also release carbon dioxide, a gas closely associated with long-term climate warming. However, the amount of carbon dioxide emitted by volcanoes is relatively small compared to human industrial activity. Over geological timescales, volcanic carbon dioxide has helped regulate Earth's temperature, contributing to cycles of warming and cooling across millions of years. On shorter timescales, volcanic ash can influence local weather almost immediately. Ash clouds can block sunlight, lowering temperatures during the day. They can disrupt air travel, reduce visibility, and affect rainfall patterns. Ash particles act as nuclei around which water droplets form. In some cases, this can enhance rainfall downwind of an eruption. In others, ash-laden clouds may suppress precipitation, depending on atmospheric conditions. Lightning is another striking phenomenon associated with volcanic eruptions. As ash particles collide within eruption clouds, they generate electrical charges. This leads to dramatic volcanic lightning, illuminating ash plumes with flashes of light. While visually stunning, these events also reveal the intense energy present in volcanic systems. Volcanic landscapes influence weather long after eruptions end. Mountains formed by volcanic activity alter wind patterns, creating rain shadows and microclimates. On one side of a volcanic range, moist air may rise and cool, producing rainfall and lush vegetation. On the other side, drier conditions may prevail. These microclimates support diverse ecosystems and have shaped human settlement patterns. Cities often develop in volcanic regions because of fertile soil, reliable water sources, and access to geothermal energy. Agriculture thrives where volcanic ash enriches the land with minerals. In places like Java, southern Italy, and parts of Central America, farming communities have flourished for centuries near volcanoes. The risk is known, yet the rewards are tangible. Crops grown in volcanic soil are often associated with rich flavors and high nutritional value, supporting local economies and cultural traditions. Volcanoes also influence the oceans, and through them, global climate. Underwater eruptions release heat and minerals into seawater. Over time, these inputs contribute to ocean chemistry and circulation. Large volcanic events can alter sea surface temperatures slightly, influencing ocean currents. Since oceans play a key role in regulating climate, even small changes can ripple through global systems. On longer geological timescales, sustained volcanic activity has helped shape Earth's atmosphere itself. Early in the planet's history, volcanic gases contributed to the formation of the atmosphere and oceans. Without this steady release of water vapor, carbon dioxide, and nitrogen. Earth might never have become hospitable to life. Volcanic plateaus formed by massive lava flows have also influenced climate by altering continental elevation and drainage patterns. The Deccan Traps in India and the Columbia River basalts in North America are examples of such features. Their formation coincided with significant environmental change. Modern science uses ice cores, tree rings, and sediment layers to trace past volcanic events. Tiny particles of ash preserved in ice and soil allow researchers to reconstruct eruption timelines and climate responses. These records deepen our understanding of how interconnected Earth's systems truly are. In today's world, satellites monitor volcanic plumes in real time. They track ash dispersion, gas emissions, and atmospheric changes. This technology helps protect aviation, inform climate models, and improve disaster preparedness. Volcanoes remind us that Earth's climate is shaped by both slow processes and sudden events. While human activity now plays a dominant role in climate change, natural forces like volcanism continue to offer context and perspective. As you rest with these thoughts, imagine volcanic clouds thinning as they drift across the sky, sunlight returning gently to the surface below. The planet adjusts, balances, and continues its quiet motion through space. As we continue, let your attention drift across the globe, moving slowly from one horizon to another. Volcanoes rise quietly in many parts of the world, each with its own shape, rhythm, and story. Some have become symbols of nations. Others remain remote and rarely seen. All of them hold memories that stretch far beyond human lifetimes. One of the most well-known volcanoes is Mount Vesuvius, resting near the Bay of Naples in Italy. Its slopes appear gentle today, dotted with towns, vineyards, and winding roads. Yet beneath this calm exterior lies a volcano whose history changed the course of archaeology and human understanding of the past. In the year 79 CE, Vesuvius erupted with tremendous force, burying the Roman cities of Pompeii and Herculaneum under ash and volcanic debris. For centuries, these cities remained hidden. When they were rediscovered, their preservation offered a detailed snapshot of daily life in ancient Rome. Homes, streets, and even footprints were frozen in time. Today, Vesuvius is closely monitored. It stands as both a natural wonder and a reminder of Earth's power. Millions of people live nearby, drawn by fertile land, economic opportunity, and deep cultural roots. Life continues alongside the volcano, balanced carefully between beauty and risk. Far across the ocean, Mount Fuji rises gracefully in Japan. Unlike Vesuvius, Fuji is known for its symmetry and quiet presence. Snow often crowns its peak, and its slopes are celebrated in art, poetry, and spiritual tradition. For centuries, Fuji has been regarded as sacred. Mount Fuji last erupted in 1707, sending ash as far as modern-day Tokyo. Since then, it has rested calmly. Pilgrims continue to climb its paths, seeking reflection and renewal. Fuji reminds us that volcanoes can inspire peace as much as awe. In the Pacific Ocean, the Hawaiian Islands offer a different volcanic story. Here, volcanoes like Mauna Loa and Klauia are formed not by tectonic plate boundaries, but by a hotspot deep within the Earth's mantle. Lava flows steadily, building land layer by layer. Mauna Loa is the largest volcano on Earth by volume and area. Its immense mass rises from the ocean floor, making it taller than Mount Everest when measured from base to summit. Yet, its eruptions are often gentle, with lava flowing slowly rather than exploding violently. Kilauea, one of the world's most active volcanoes, has provided scientists with decades of observation. Its lava lakes, glowing softly at night, reveal the constant movement beneath Earth's crust. These volcanoes are deeply woven into Hawaiian culture, where they are associated with creation, transformation, and respect for nature. Moving northward, Iceland emerges as a land shaped almost entirely by volcanic forces. Here, fire and ice exist side by side. Volcanoes rise beneath glaciers, and eruptions sometimes melt ice rapidly, creating powerful floods known as J-clopes. A G-Volcanoes, a volcano hidden beneath a glacier, became widely known in 2010 when its eruption disrupted air travel across Europe. Fine ash spread through the atmosphere, grounding flights for days. While the eruption caused limited damage on the ground, it demonstrated how interconnected modern systems are. Icelanders have learned to live closely with volcanoes. Geothermal energy heats homes, generates electricity, and supports a strong, sustainable economy. Hot springs and volcanic landscapes also attract travelers from around the world, blending tourism with natural science and relaxation. In Indonesia, one of the most volcanically active regions on Earth, Mount Merapi stands as both a guardian and a challenge. Its name means mountain of fire. Merapi erupts frequently, shaping the land and affecting nearby communities. Despite the danger, people return after eruptions, rebuilding homes and farms. Volcanic soil supports rice fields and agriculture that sustain millions. Traditional beliefs, rituals, and modern monitoring work together to guide life around the mountain. Another Indonesian giant, Krakatoa, offers a story heard around the world. In 1883, Krakatoa erupted with extraordinary force. The explosion was one of the loudest sounds ever recorded, heard thousands of kilometers away. Tsunamis followed, reshaping coastlines and claiming many lives. The eruption also affected global climate, cooling temperatures, and producing vivid sunsets for years afterward. Today, a new volcanic island, Anak Krakatau, or Child of Krakatau, continues to grow from the sea, a reminder that Earth is always in motion. In Africa, Mount Kilimanjaro rises above the plains of Tanzania. Though currently dormant, it is a volcanic massif composed of several cones. Its snow-capped summit near the equator has long captured the imagination of explorers and writers. Kilimanjaro's glaciers are shrinking, offering scientists insight into climate change. The mountain remains a symbol of endurance and quiet grandeur, drawing travelers seeking both challenge and inspiration. Across the Andes in South America, volcanoes line the western edge of the continent. Cotopaxi in Ecuador is one of the tallest active volcanoes in the world. Its nearly perfect cone rises above cloud forests and grasslands. The Andes volcanoes have shaped civilizations for thousands of years. Ancient cultures adapted to high altitudes and volcanic landscapes, developing agriculture, architecture, and trade routes in challenging conditions. Even beneath the oceans, famous volcanoes coexist. Submarine volcanoes, like axial seamount in the Pacific, are monitored by instruments placed on the seafloor. Their eruptions rarely make headlines, yet they play a major role in shaping Earth's crust. These underwater volcanoes remind us that most volcanic activity happens out of sight, quietly renewing the planet's surface without drama. Each volcano carries a unique story shaped by geology, culture, and time. Together, they form a global network of natural processes that continue regardless of human attention. As you rest, imagine these mountains standing peacefully under the stars, their internal heat balanced by the cool night air. They are neither rushing nor waiting. They simply exist. As we move gently forward, let the image of glowing lava slowly cool in your mind. What begins as heat and motion eventually becomes still ground beneath forests, fields, and cities. One of the quiet wonders of volcanoes is not found in eruption, but in what follows afterward. When lava flows across the land, it looks destructive at first. Vegetation is covered. Soil disappears. Yet this is only one moment in a much longer story. Over time, volcanic rock begins to break down. Wind, rain, temperature changes, and living organisms slowly transform hardened lava into soil. Volcanic soil is often among the most fertile on Earth. It contains essential minerals such as potassium, phosphorus, calcium, and magnesium. These nutrients support plant growth, agriculture, and complex ecosystems. What once emerged as molten rock eventually becomes the foundation of life. This process can take decades or centuries, but it is remarkably consistent. Around the world, some of the most productive farming regions sit on ancient volcanic deposits. Crops grow strong roots. Harvests are reliable. Communities develop deep connections to the land. In places like southern Italy, vineyards thrive on volcanic slopes. Grapes grown in this soil are often described as having unique flavors. Shaped by mineral-rich ground and microclimates created by elevation and terrain. Wine production here blends geology, culture, and economy into a single tradition. Similarly, coffee grown on volcanic soil in regions of Central America, East Africa, and Southeast Asia is prized worldwide. The steady drainage, mineral balance, and altitude provided by volcanic landscapes create ideal growing conditions. These regions support both local livelihoods and global trade. Beyond agriculture, volcanoes create habitats for diverse ecosystems. As land cools and soil forms, pioneer species appear. Mosses, lichens, and grasses are often the first to take hold. Their roots and organic matter help further break down rock, accelerating soil development. Over time, shrubs and trees follow. Forests spread across slopes that were once bare. In Hawaii, scientists have observed this process in detail, watching lava fields transform gradually into rich rainforests. Life adapts patiently, guided by time rather than urgency. Volcanic landscapes also shape water systems. Porous lava rock allows rainwater to filter underground, forming aquifers. These natural reservoirs supply fresh water to communities and ecosystems. Springs emerge where water meets less permeable rock layers. In Iceland, volcanic terrain supports geothermal features that heat water naturally. Hot springs and geysers emerge, providing warmth and energy in an otherwise cold environment. These systems support both daily life and relaxation, blending natural science with wellness and tourism. Human settlements often grow near volcanoes because of these advantages. Fertile soil, fresh water, and geothermal energy offer stability and opportunity. Even after destructive eruptions, people frequently return, rebuilding homes and fields. This pattern is visible across history. Ancient civilizations in Mesoamerica, the Andes, and the Mediterranean developed near volcanic regions. They learned to read the land, interpret signs, and pass knowledge through generations. Volcanoes also influence biodiversity by creating isolated environments. Islands formed by volcanic activity often evolve unique species found nowhere else on Earth. Without land connections to continents, plants and animals adapt independently. The Galapagos Islands are a well-known example. Formed entirely by volcanic activity, they host species that inspired early studies of evolution. Lava fields, cinder cones, and volcanic soils created varied habitats within a small area. On land, volcanic mountains create elevation gradients. As altitude increases, temperature and vegetation change. This allows multiple ecosystems to exist close together, from tropical forests at lower levels to alpine environments higher up. Animals adapt to these conditions. Birds, insects, and mammals find niches suited to their needs. Over time, volcanic regions become centers of ecological diversity. Even in extreme environments, life finds ways to persist. Near active volcanoes, heat-loving microorganisms thrive in hot springs and fumaroles. These extremophiles offer insight into how life might exist on other planets with volcanic activity. Scientists study these organisms to understand early life on Earth and the potential for life elsewhere in the universe. In this way, volcanoes contribute not only to ecosystems, but also to education and exploration beyond our planet. Volcanic ash plays a role as well. Fine ash particles carried by wind can settle far from eruption sites. When mixed with soil, ash improves texture and nutrient content. In some regions, ash layers are deliberately preserved for agriculture. Japan's rice fields, for example, benefit from volcanic deposits that improve soil structure and water retention. Over centuries, this has supported dense populations and complex societies. Volcanoes also shape coastlines. Lava flows, reaching the sea, create new land, extending islands and shores. Over time, waves break down this rock, forming beaches and reefs. Coastal environments support fisheries, tourism, and marine ecosystems. In Hawaii, new land continues to form as lava enters the ocean. Steam rises, rock cools, and the island slowly grows. This quiet expansion reminds us that Earth is not static, but always becoming. While volcanoes can bring danger, they also bring renewal. Destruction and creation exist together, part of a natural cycle far older than humanity. As you rest with this idea, imagine a dark lava field under gentle rain. Tiny plants begin to grow. Years pass, soil deepens, trees rise. Life returns, steady and assured. As we continue, imagine standing at a respectful distance from a volcanic mountain at rest. There is no smoke, no sound, only the sense of depth beneath the ground. Though volcanoes may appear still for long periods, scientists know they are never truly asleep. Beneath the surface, slow movements continue, and careful observation helps us understand them. Volcanology is the scientific study of volcanoes. It combines geology, chemistry, physics, and technology to interpret signals from deep within the earth. The goal is not to control volcanoes, but to listen to them. One of the most important tools used to monitor volcanoes is the seismometer. These sensitive instruments detect small earthquakes caused by magma moving underground. As molten rock rises or shifts, it cracks surrounding rock, creating vibrations. By analyzing these patterns, scientists can infer changes in volcanic systems. Not all volcanic earthquakes feel the same. Some are sharp and sudden. Others are slow and rhythmic, known as harmonic tremors. These gentle vibrations often indicate magma flowing steadily through channels. Their presence can suggest that a volcano is becoming more active. Ground deformation is another key signal. As magma accumulates beneath a volcano, it can cause the ground to swell slightly. Scientists use GPS stations and satellite radar to measure these changes with remarkable precision. Even a few centimeters of uplift can provide valuable information. In some regions, satellites pass over volcanoes regularly, using radar to detect surface movement. This method allows scientists to monitor remote or dangerous volcanoes without placing people nearby. It also helps track changes over time, revealing long-term trends. Gas emissions offer further clues. Volcanoes release gases such as water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide. Changes in the type or amount of gas can indicate magma rising closer to the surface. Scientists measure these gases using ground instruments, drones, and satellites. Some gases are invisible, yet their presence can be detected by sensors tuned to specific wavelengths. When sulfur dioxide levels increase significantly, it often signals increased volcanic activity. Temperature monitoring is another gentle form of observation. Thermal cameras detect heat changes on a volcano's surface. New heat may indicate magma movement, rising gases, or changes in hydrothermal systems. In volcanic regions with hot springs and fumaroles, water chemistry is closely monitored. Subtle changes in acidity, mineral content, or temperature can reveal shifts underground. These quiet measurements provide early warnings without disturbing the landscape. Volcano observatories around the world coordinate these efforts. Organizations such as the United States Geological Survey, the Japan Meteorological Agency, and similar institutions in Iceland, Italy, and Indonesia maintain constant watch over active volcanoes. These observatories do more than collect data. They communicate with local authorities, develop hazard maps, and help communities prepare for possible eruptions. Education and preparedness are as important as technology. Hazard maps show areas most likely to be affected by lava flows, ashfall, landslides, or volcanic gases. These maps guide urban planning, evacuation routes, and emergency response. They help reduce risk while allowing people to continue living near volcanoes. In many regions, traditional knowledge complements scientific monitoring. Indigenous communities have long observed signs of volcanic change, such as altered springs, unusual animal behavior, or changes in vegetation. This knowledge is increasingly respected and integrated into modern approaches. Despite advances in technology, predicting exact eruption timing remains challenging. Volcanoes are complex systems influenced by many variables. Instead of precise predictions, scientists focus on probability and preparedness. This approach emphasizes calm readiness rather than fear. Communities learn what to expect, how to respond, and when to move, if necessary. Over time, this shared understanding builds trust between scientists and residents. Modern communication plays a vital role. Alerts are shared through radio, text messages, and online platforms. Clear language and consistent updates help reduce confusion and anxiety. Volcano monitoring also contributes to broader scientific understanding. Data collected helps refine models of Earth's interior, plate tectonics, and geothermal systems. These insights support education, energy development, and environmental research. In some regions, geothermal energy derived from volcanic heat provides clean, renewable power. Monitoring volcanic systems helps ensure this energy is used safely and sustainably, supporting local economies and reducing reliance on fossil fuels. Volcanoes also attract travelers seeking natural beauty and adventure. Monitoring ensures that tourism can coexist with safety. Trails, observation points, and guided experiences allow people to appreciate without unnecessary risk. This balance between curiosity and caution reflects a broader relationship with nature. Volcanoes remind us that the Earth is active, dynamic, and worthy of respect. As you rest now, imagine scientists quietly watching instruments as night falls. Screens glow softly, data streams in steadily. Beneath the ground, the volcano continues its slow movements, observed but undisturbed. As we continue gently onward, allow the science to soften into story. Long before instruments, satellites, or seismic charts, people lived beside volcanoes and tried to understand them through meaning rather than measurement. Fire rising from the ground inspired awe, fear, reverence, and creativity. Across cultures, volcanoes became more than geology. They became characters in the human imagination. In ancient times, volcanoes were often seen as the homes of gods or powerful spirits. Their unpredictable nature felt alive, intentional, and purposeful. When the ground shook or fire emerged, it was interpreted as communication rather than coincidence. In Roman mythology, Mount Etna in Sicily was believed to be the forge of Vulcan, the god of fire and metalworking. Deep beneath the mountain, Vulcan and the Cyclopes were said to craft weapons for the gods. The sounds of eruptions were imagined as hammering and glowing lava as molten metal poured from divine workshops. This story reflects how humans used familiar ideas to explain unfamiliar forces. Fire and craftsmanship were known. By linking them to volcanoes, people made sense of overwhelming natural power in human terms. In Hawaiian culture, volcanoes are closely associated with Pl, the goddess of fire, lightning, and creation. Pl is not portrayed simply as destructive. She is creative, passionate, and ever-moving. Her lava flows shape the islands, forming new land and altering coastlines. Stories of Peel emphasize respect for nature. Taking lava rocks is often discouraged, not only for cultural reasons, but as a symbol of balance between humans and the land. These beliefs continue to influence modern attitudes toward conservation and tourism. In Japan, volcanoes appear frequently in folklore and spiritual practice. Mount Fuji, though currently quiet, has long been regarded as sacred. Shrines and pilgrimages honor the mountain as a place of purification and reflection. Eruptions in Japan were historically interpreted as expressions of imbalance, calling for rituals to restore harmony between people, nature, and the spiritual world. This perspective encouraged collective responsibility rather than individual blame. In Mesoamerican civilizations, volcanoes played a central role in cosmology. The Aztecs viewed nearby volcanic peaks as protectors and providers. Mountains were seen as sources of water, fertility, and life. Legends surrounding Popocatépetl and Iztaccíhuatl in Mexico tell a story of love, loss, and eternal watchfulness. These two volcanoes are said to represent a warrior and a princess, transformed into mountains that stand side by side. Their silhouettes against the sky continue to inspire poetry and art. In Indonesia, where volcanoes are a part of daily life, cultural practices blend respect, adaptation, and acceptance. Ceremonies are held to honor mountain spirits and ask for protection. These rituals do not deny scientific understanding, but coexist alongside it. Volcanoes have also shaped language. Words like volcanic, eruption, and lava are used metaphorically to describe emotion, creativity, and social change. This reflects how deeply volcanic imagery resonates with human experience. Artists have long been drawn to volcanic landscapes. Painters depict glowing flows and dramatic skies. Writers describe eruptions as moments of revelation or transformation. Even composers have sought to capture the slow tension and release associated with volcanic activity. The atmosphere itself became a canvas, subtly altered by distant eruptions. Art and geology intersected without intention. Literature often uses volcanoes to symbolize hidden forces beneath calm surfaces. A quiet mountain may represent suppressed emotion, potential change, or the passage of time. When an eruption occurs in a story, it often marks a turning point. Volcanoes also appear in modern film and popular media, sometimes exaggerated for spectacle. While these portrayals are not always scientifically accurate, they reflect continued fascination. Fire emerging from Earth remains compelling, even in an age of technology. Beyond myth and art, volcanoes influence cultural identity. Regions shaped by volcanic landscapes often develop strong local traditions tied to land and memory. Food, architecture, and festivals reflect adaptation to terrain and climate. In Italy, towns near volcanoes celebrate harvests grown in volcanic soil. In Iceland, hot springs and geothermal baths are part of daily life, blending geology with relaxation and wellness. These practices support tourism, economy, and community. Volcanoes also remind societies of impermanence. Cities buried by ash teach lessons about vulnerability and resilience. These stories encourage humility and long-term thinking. At the same time, volcanoes symbolize renewal. After destruction comes fertile ground. After silence comes growth. This cycle mirrors human experiences of change and recovery. In modern education, volcanoes serve as gateways to science. They spark curiosity in students, leading to studies in earth science, physics, chemistry, and environmental systems. Curiosity becomes a bridge between wonder and understanding. As you rest now, imagine ancient people sitting beneath a dark sky, watching a distant glow on the horizon. Without knowing its mechanics, they felt its presence and gave it meaning. Today, we understand more, yet the sense of awe remains. Science has not replaced wonder, it has deepened it. As we continue, let your imagination drift away from Earth itself, floating gently outward into space. The same forces that shape volcanoes here are not unique to our planet. Across the solar system, worlds, large and small, bear the marks of volcanic activity, reminding us that geology is a universal language written in stone, ice, and fire. Volcanism is not limited to molten rock alone. On other planets and moons, similar processes occur with different materials, temperatures, and outcomes. Scientists use the term volcanism broadly to describe the movement of material from a planet's interior to its surface. Whether that material is lava, ice, or gas. One of the most striking volcanic worlds is Io, a moon of Jupiter. Io is the most volcanically active body known in the solar system. Its surface is constantly reshaped by eruptions, leaving little time for impact craters to accumulate. Io's intense activity is driven by tidal forces. As it orbits Jupiter, gravity stretches and squeezes the moon repeatedly. This constant flexing generates heat deep inside, melting rock and driving volcanic eruptions. Some of Io's volcanoes send plumes hundreds of kilometers above the surface. These eruptions are so powerful that they can be detected by spacecraft passing nearby. The colors seen on Io's surface come from sulfur and other volcanic materials, painting the moon in vivid yellows, reds, and blacks. Unlike Earth's volcanoes, Io's eruptions are not shaped by plate tectonics. Instead, they reveal how gravitational energy alone can fuel geological activity. This discovery expanded scientific understanding of how planets and moons evolve. Venus, often called Earth's twin because of its similar size, also shows strong evidence of volcanism. Its surface is covered with vast lava plains, volcanic domes, and shield volcanoes. Some of these features rival or exceed the size of Earth's largest volcanic structures. Venus's dense atmosphere and extreme surface temperatures make direct observation challenging. However, radar mapping has revealed landscapes shaped by flowing lava. Scientists believe that Venus experienced widespread volcanic resurfacing in the past, renewing much of its surface. There is also evidence that Venus may still be volcanically active today. Changes in atmospheric chemistry and surface features suggest that eruptions could still occur, though confirmation remains difficult. Studying Venus helps scientists understand how similar planets can follow very different evolutionary paths. Mars offers another perspective on volcanism. The red planet is home to the largest volcano in the solar system, Olympus Mons. This enormous shield volcano rises about 22 kilometers above the surrounding plains. Nearly 3 times the height of Mount Everest. Olympus Mons formed over millions of years as lava flowed repeatedly from a single hotspot. Because Mars lacks active plate tectonics, the volcano did not move away from its magma source. Instead, it grew taller and broader with each eruption. Although Mars appears volcanically quiet today, its surface preserves a long history of volcanic activity. Lava flows, volcanic cones, and ash deposits reveal a planet that was once geologically dynamic. These features help scientists reconstruct Mars's climate history and potential habitability. Volcanism on Mars may have contributed to the presence of water in the past. Heat from volcanic activity could have melted ice, creating temporary rivers or lakes. Volcanic gases may also have thickened the atmosphere, allowing liquid water to exist on the surface. Beyond Mars, icy moons show a different kind of volcanism, known as cryovolcanism. Instead of molten rock, these eruptions involve water, ammonia, or methane. Enceladus, a moon of Saturn, is one of the most fascinating examples. Cracks near its south pole release plumes of water vapor and ice particles into space. These geysers are driven by internal heat and tidal forces, similar in principle to what expressed through ice rather than fire. These plumes suggest the presence of a subsurface ocean beneath Enceladus's icy crust. The water contains organic compounds, making this moon a key target in the search for life beyond Earth. Cryovolcanism here blurs the line between geology and biology. Europa, another moon of Jupiter, also shows signs of cryovolcanic activity. Its cracked, icy surface hints at a warm ocean beneath. Material from below may occasionally reach the surface, refreshing the ice and revealing chemical clues. Even Pluto, once thought to be a frozen and inactive world, shows possible evidence of cryovolcanic features. Large domes and smooth plains suggest that internal processes may still shape its surface, despite its distance from the Sun. Studying volcanism across the solar system helps scientists understand the fundamental processes that shape planets. It reveals how internal heat, gravity, and composition interact over time. These discoveries also influence how scientists think about habitability. Volcanic activity can create energy sources, recycle materials, and support chemical complexity. On Earth, life may have originated near volcanic or hydrothermal environments. Similar settings elsewhere could offer comparable opportunities. Space missions play a crucial role in this exploration. Orbiters, landers, and flyby spacecraft collect images, measure chemical signatures, and detect heat anomalies. Each mission adds another piece to the puzzle. Volcanoes beyond Earth remind us that our planet is part of a much larger system. The same forces shaping familiar mountains also sculpt distant worlds we may never visit in person. As you rest now, imagine drifting past these volcanic worlds, each quietly expressing its inner heat in its own way. Fire becomes ice, lava becomes vapor. The language changes, but the meaning remains. As we continue gently onward, let us return fully to Earth, carrying with us the wider perspective of time and space. Volcanoes are neither enemies nor guardians. They are natural systems, powerful yet predictable in their own rhythms. Understanding volcanic hazards is not about fear, but about awareness, preparation, and calm coexistence. Volcanic hazards take many forms, and not all involve dramatic explosions. Some develop slowly and quietly, while others move with surprising speed. Each hazard reflects a different interaction between heat, rock, gas, and gravity. One of the most familiar hazards is lava flow. Lava moves when molten rock reaches the surface and begins to travel downhill. Its speed depends on temperature, composition, and slope. Some lava flows creep forward slowly, allowing time for evacuation. Others, especially those with lower viscosity, can move more quickly. Although lava flows are destructive to buildings and infrastructure, they rarely cause loss of life when communities are prepared. Their predictable paths and visible movement make them among the more manageable volcanic hazards. Ash fall is far more widespread. Fine volcanic ash can travel hundreds or even thousands of kilometers from an eruption. Ash clouds affect air quality, reduce visibility, and disrupt transportation, especially aviation. When ash settles, it can damage crops, contaminate water supplies, and place heavy loads on rooftops. Yet ash also brings long-term benefits by enriching soil. The challenge lies in managing its immediate impact while recognizing its eventual contribution to fertility. Pyroclastic flows are among the most dangerous volcanic phenomena. These fast-moving currents of hot gas, ash, and rock fragments race down volcano slopes at incredible speeds. Their temperatures can exceed hundreds of degrees, and they can travel many kilometers in minutes. Because of their speed and intensity, pyroclastic flows require strict exclusion zones. Monitoring and early warnings are essential for reducing risk. Understanding where these flows are likely to travel helps authorities plan safe areas and evacuation routes. Volcanic gases pose another hazard, often invisible but significant. Gases such as sulfur dioxide, carbon dioxide, and hydrogen sulfide can accumulate in low-lying areas. In high concentrations, they can irritate lungs, harm vegetation, or displace oxygen. Carbon dioxide is particularly dangerous because it is heavier than air and colorless. In rare cases, it can collect in valleys or enclosed spaces. Monitoring gas levels and educating communities about ventilation and warning signs helps prevent accidents. Lahars, or volcanic mudflows, form when volcanic material mixes with water. This water may come from heavy rain, melting snow, or crater lakes. Lahars flow rapidly along river valleys, carrying debris and reshaping landscapes. Unlike lava flows, lahars can occur long after an eruption has ended. They can travel far from the volcano itself, affecting areas that may not expect volcanic hazards. Early warning systems and land use planning are crucial in the HER-prone regions. Volcanic landslides and collapses also present risks. Over time, volcanic cones can become unstable due to internal changes or erosion. When large sections collapse, they can trigger debris avalanches or tsunamis if they enter the sea. Despite these hazards, millions of people live near volcanoes safely. This is possible because of science, communication, and community planning. Hazard zones are mapped carefully, and risk levels are updated regularly. Evacuation planning is a key part of safety. Clear routes, designated shelters, and regular drills help communities respond calmly when alerts are issued. Familiarity reduces panic and allows people to act decisively. Education plays a central role. When people understand how volcanoes behave, they are better able to interpret warnings and follow guidance. Schools, community programs, and public information campaigns help build this understanding over time. Technology continues to improve volcanic safety. Satellite monitoring, real-time data sharing, and automated alerts allow for faster responses. Mobile technology helps spread information quickly, even in remote areas. International cooperation is also important. Volcanic ash does not respect borders, and shared airspace requires shared responsibility. Scientists collaborate across countries to track eruptions and manage impacts on aviation and climate. Economic planning helps communities recover after eruptions. Insurance systems, disaster relief funds, and infrastructure investment support resilience. Tourism often returns once conditions stabilize, drawn by renewed landscapes and scientific interest. Culturally, many societies integrate volcano awareness into daily life. Stories, rituals, and traditions pass knowledge through generations. This cultural continuity reinforces respect for the land and its rhythms. Living with volcanoes teaches patience and adaptability. It reminds us that absolute control is neither possible nor necessary. Instead, balance comes from understanding, preparation, and humility. As you rest now, imagine a quiet village near a volcano at night. Lights glow softly. Instruments hum gently in the distance. The mountains stand still, observed and respected. As we move gently forward, let us explore a quieter side of volcanoes, one that hums beneath the surface rather than roaring into the sky. Beyond their dramatic eruptions, volcanoes offer something deeply valuable to human societies: energy, resources, and long-term opportunity. In this part, we drift into the calm relationship between volcanic heat and human ingenuity. Deep beneath volcanic regions, the Earth stores immense thermal energy. This heat is a remnant of our planet's formation and a product of ongoing radioactive decay. In areas where magma lies closer to the surface, that heat becomes accessible. This is the foundation of geothermal energy, one of the most stable and sustainable forms of renewable power. Unlike wind or solar energy, geothermal systems provide constant output day and night, regardless of weather. This reliability makes geothermal energy especially valuable for modern economies seeking clean, dependable electricity. Countries with active or recent volcanic activity often lead in geothermal development. Iceland is one of the most well-known examples. Nearly all of its electricity and heating come from renewable sources, with geothermal power playing a central role. Hot water circulates naturally beneath the island, heating homes, greenhouses, and public spaces. In places like New Zealand, geothermal energy has long been integrated into daily life. The Māori people historically used geothermal heat for cooking and bathing, and today, the same regions support modern power plants that feed national grids. The Philippines, Indonesia, Kenya, and parts of the United States also harness geothermal energy from volcanic zones. These projects support local economies, reduce dependence on imported fuels, and lower greenhouse gas emissions. Beyond electricity, volcanic heat supports direct-use applications. Warm groundwater heats buildings, dries crops, and supports Aquaculture. In colder climates, geothermal district heating systems provide efficient warmth during long winters. Volcanic regions also offer valuable mineral resources. Magmatic processes concentrate metals such as copper, gold, silver, and nickel. Many of the world's major mining districts formed near ancient volcanic systems. These resources support global industries, from construction and electronics to renewable technology and transportation. Copper wiring, lithium batteries, and rare earth elements all trace parts of their geological origins to volcanic activity. Volcanic soils further contribute to economic stability through agriculture. Over time, weathered volcanic ash creates soils rich in nutrients like potassium, phosphorus, and trace minerals. These fertile lands support high crop yields and diverse farming systems. Regions such as southern Italy, Japan, Java, and Central America have farmed volcanic soils for centuries. Vineyards, coffee plantations, rice paddies, and fruit orchards thrive in these landscapes. Connecting geology directly to food, security, and culture. Tourism is another major economic benefit of volcanoes. Travelers are drawn to volcanic landscapes for their beauty, uniqueness, and sense of wonder. Crater lakes, lava fields, hot springs, and volcanic beaches create unforgettable experiences. Carefully managed tourism provides income while protecting fragile environments. Guided hikes, educational centers, and observation points allow visitors to learn while minimizing risk. In many regions, volcano tourism supports local businesses and conservation efforts. Volcanoes also inspire wellness tourism. Natural hot springs, heated by geothermal activity, are used for relaxation, therapy, and health traditions. These destinations blend nature, luxury, and cultural heritage. From a technological perspective, volcanic regions drive innovation. Drilling techniques developed for geothermal energy improve engineering knowledge. Monitoring systems refine data, analysis, and sensor technology. Education and research flourish around volcanoes. Universities and research institutes study volcanic systems to better understand Earth processes. These studies contribute to broader fields such as climate science, materials science, and planetary geology. Volcanic analog environments on Earth even help prepare for space exploration. Lava tubes, volcanic plains, and extreme conditions resemble landscapes found on the Moon and Mars. Studying them helps scientists plan future missions and habitats. Economically, investing in volcanic regions requires careful planning. Infrastructure must account for hazards while maximizing benefits. When done thoughtfully, this balance creates resilient communities with diverse income sources. Volcano-based economies often emphasize sustainability. Renewable energy, ecotourism, and local agriculture align with global goals for environmental responsibility. These regions demonstrate how living with nature can support long-term prosperity. Culturally, volcanoes shape identity and tradition. Festivals, art, and storytelling reflect respect for the land's power. These cultural expressions strengthen social cohesion and continuity. As you rest now, imagine warm water rising gently through stone, lighting homes without smoke, feeding crops without chemicals, and welcoming travelers seeking calm and connection. All of this energy flows quietly from deep within the earth. Now, as the pace remains slow and gentle, let us drift away from Earth for a while. Imagine lifting softly above the clouds, past the atmosphere, and into the quiet openness of space. Volcanoes are not only part of our planet's story. They are scattered throughout the solar system, shaping distant worlds in ways both familiar and astonishing. Volcanism is a universal process. Wherever a planetary body has internal heat, pressure, and a pathway to release that energy, volcanoes can form. By studying volcanic activity beyond Earth, scientists learn not only about those worlds, but also about the deep mechanics that once shaped our own planet in its earliest ages. One of the most extraordinary volcanic worlds is Io, a moon of Jupiter. Io is the most volcanically active body ever observed. Its surface is constantly reshaped by hundreds of active volcanoes, some erupting lava fountains hundreds of kilometers high. Unlike Earth, Io's volcanic energy does not come primarily from radioactive heat. Instead, it comes from tidal forces. Jupiter's immense gravity stretches and squeezes Io as it orbits, creating friction deep inside the moon. That constant flexing generates heat, melting rock, and driving relentless volcanic eruptions. From a distance, Io appears painted in shades of yellow, orange, red, and black. These colors come from sulfur compounds deposited by eruptions. Lava flows spread rapidly across the surface, freezing almost instantly in the cold vacuum of space. There is no water, no atmosphere like Earth's, and no life as we know it on Io. Yet, its volcanoes remind us that geological activity does not require oceans or air. Energy alone is enough. Moving outward, we encounter another intriguing volcanic world, Enceladus, a small moon of Saturn. At first glance, Enceladus seems quiet and icy. But beneath its frozen crust lies a hidden ocean warmed by internal heat. Instead of lava, Enceladus experiences cryovolcanism. Cryovolcanoes erupt water, ice particles, and dissolved gases rather than molten rock. Enormous geysers shoot plumes of water vapor into space through cracks near the moon's south pole. These plumes feed Saturn's E-ring and provide direct samples of the moon's interior. Spacecraft have flown through them, detecting water, salts, organic molecules, and even hints of chemical reactions that, on Earth, support life. Cryovolcanism expands our understanding of what volcanic activity can be. Heat interacting with different materials produces different expressions. Yet the underlying process remains the same: internal energy seeking release. Another icy moon, Europa, also shows signs of volcanic-like activity beneath its frozen surface. Europa's ocean lies under kilometers of ice, warmed by tidal heating from Jupiter. While surface eruptions are rare or subtle, fractures and ridges suggest ongoing movement below. Some scientists believe that Europa's seafloor may host hydrothermal vents, similar to those found along Earth's mid-ocean ridges. On Earth, such vents support rich ecosystems independent of sunlight. This possibility makes Europa one of the most intriguing places in the search for life beyond our planet. Mars, quieter now, carries scars of immense, ancient volcanism. The planet is home to Olympus Mons, the largest volcano in the solar system. It rises about 3 times higher than Mount Everest and spans an area larger than many countries. Olympus, Mons, formed differently from Earth's volcanoes. Mars lacks active plate tectonics, so magma rose repeatedly through the same location over millions of years. Each eruption added new layers, building a vast shield volcano. Though dormant today, Mars's volcanic past shaped its atmosphere, surface, and climate. Lava flows created plains, released gases, and influenced the planet's ability to hold water long ago. Nearby, the Tharsis region contains multiple massive volcanoes aligned in ways that suggest deep mantle activity. These structures hint at a once dynamic interior that slowly cooled over time. Venus offers another volcanic mystery. Similar in size and composition to Earth, Venus shows widespread volcanic features across its surface. Radar mapping reveals lava plains, shield volcanoes, and enormous volcanic rises. Because Venus's thick atmosphere hides its surface from direct view, studying its volcanoes requires advanced technology. Some evidence suggests that Venus may still be volcanically active today, with eruptions reshaping its surface on geological timescales. Volcanism on Venus may play a role in its extreme climate. Massive eruptions could have released greenhouse gases, contributing to the planet's intense heat. Understanding this connection helps scientists model climate change processes, both on Venus and Earth. Even distant dwarf planets show volcanic traces. Pluto, once thought completely frozen, displays evidence of cryovolcanic flows. Smooth plains and possible ice volcanoes suggest that internal heat lingered longer than expected. These discoveries challenge earlier assumptions that small worlds cool quickly and become inactive. Instead, many bodies retain warmth through unique mechanisms, allowing geological processes to persist. Studying extraterrestrial volcanoes also informs space exploration. Volcanic materials provide clues about internal composition. Eruption patterns reveal how heat moves through planetary interiors. Volcanic landscapes serve as training grounds for astronauts on Earth. Lava fields resemble surfaces found on the Moon and Mars, helping prepare for future missions. Lava tubes, formed by flowing lava, may one day shelter human explorers from radiation. Beyond science, there is something quietly humbling about volcanoes across the solar system. They remind us that Earth is not alone in its restless energy. Our planet's fire is part of a broader cosmic rhythm. As you imagine these distant worlds glowing faintly in the dark, picture volcanoes silently shaping landscapes no human may ever walk upon. Even there, deep beneath frozen crusts or barren plains, planets breathe and move. As we drift gently back toward Earth, let the image of distant volcanic worlds slowly fade. Now, imagine our own planet again, quietly turning beneath a thin blue atmosphere. Volcanoes here do far more than shape mountains and islands. Over deep time, they have helped regulate Earth's climate, influence the air we breathe, and guide the long rhythm of planetary balance. Volcanoes act as both creators and disruptors of climate. Their influence can feel subtle over millions of years or sudden and dramatic within a single season. Understanding this dual role helps explain why volcanic activity is woven so deeply into Earth's environmental story. When a volcano erupts, it releases gases trapped deep within the planet. The most abundant of these is water vapor, followed by carbon dioxide, sulfur dioxide, and smaller amounts of other gases. Each interacts with the atmosphere in different ways. Carbon dioxide, released steadily by volcanoes over geological time, is one of the key ingredients that keeps Earth warm enough for life. Early in Earth's history, when the sun was fainter, volcanic carbon dioxide helped prevent the planet from freezing completely. In this way, volcanism supported the long-term habitability of Earth. However, volcanic carbon dioxide is released slowly on human timescales. Even large eruptions contribute far less carbon dioxide than modern industrial activity. This distinction is important for understanding today's climate changes. Sulfur dioxide behaves differently. When injected high into the atmosphere during explosive eruptions, it reacts with water vapor to form tiny sulfate aerosols. These particles reflect sunlight back into space, temporarily cooling the planet. One of the most famous examples is the eruption of Mount Pinatubo in 1991. This eruption sent massive amounts of sulfur dioxide into the stratosphere, leading to a measurable drop in global temperatures of about 0.5 degrees Celsius for more than a year. Earlier eruptions had even more dramatic effects. The eruption of Tambora in 1815 caused what became known as the Year Without a Summer. Crops failed across parts of Europe and North America, leading to food shortages and social disruption. These events remind us that volcanoes can influence not only natural systems, but human history as well. Weather patterns shift, harvests change, and societies adapt in response to forces rising from deep underground. Volcanic ash also plays a role in climate and ecosystems. Fine ash particles can remain suspended in the atmosphere, altering sunlight and precipitation patterns. When ash settles, it enriches soils with minerals, eventually supporting agriculture. Many of the world's most fertile regions owe their richness to ancient volcanic deposits. From the slopes of Mount Vesuvius to the highlands of Indonesia, volcanic soils support dense populations and productive farming. In this way, volcanoes balance destruction with renewal. Eruptions may devastate landscapes in the short term, but over time, they build the foundation for life to return. Volcanoes also influence Earth's oceans. Submarine eruptions release heat and minerals into seawater, supporting unique ecosystems around hydrothermal vents. These environments host organisms that rely not on sunlight, but on chemical energy. Such ecosystems offer clues about the origins of life on Earth. They suggest that life may have begun in volcanic environments where energy and chemical diversity were abundant. Volcanic activity also contributes to the formation of continents. Over millions of years, eruptions add material to Earth's surface. Island chains like Hawaii demonstrate this process clearly. As tectonic plates move over hotspots, new volcanoes form, grow, erode, and eventually sink back into the sea. This cycle shapes ocean geography and influences global ocean currents. Ocean currents, in turn, regulate climate by distributing heat around the planet. Thus, volcanic activity indirectly affects weather patterns far beyond the eruption site. Deep beneath the surface, volcanoes participate in Earth's carbon cycle. Carbon dioxide, released by eruptions, is eventually absorbed by oceans, plants, and rocks. Through processes like weathering and sedimentation, carbon is stored and recycled over millions of years. This slow cycling acts as a planetary thermostat, preventing extreme temperature swings over geological time. Without volcanism, Earth might either freeze solid or become too hot for life. Volcanoes also affect the atmosphere's composition. Gases released during eruptions contribute to the formation of clouds and influence atmospheric chemistry. Over Earth's history, volcanic gases helped shape the oxygen-rich atmosphere we depend on today. Early volcanic emissions created an environment where chemical reactions could occur, eventually supporting the emergence of life. Later, interactions between volcanic gases and early organisms helped stabilize atmospheric conditions. From a modern perspective, volcanoes are carefully monitored for their climatic impacts. Satellites track ash clouds, sulfur emissions, and atmospheric changes in real time. This technology helps protect aviation, agriculture, and public health. Despite their power, volcanoes operate on timescales much longer than a human lifetime. Their influence reminds us that Earth is a living system, constantly adjusting through processes both violent and gentle. As you rest with these thoughts, imagine Earth breathing slowly. Volcanoes serve as part of that breath, releasing pressure, renewing the surface, and maintaining balance across ages. As we arrive at the final stretch of this calm journey, imagine standing at a gentle distance from a volcano at rest. The air is still. The ground feels solid beneath your feet. Nothing moves, and yet everything is alive with possibility. This is how volcanoes have always existed alongside humanity, silent most of the time, powerful enough to reshape worlds when they awaken. From the earliest human societies, volcanoes inspired awe, fear, and reverence. Ancient cultures often saw them as gateways between worlds, homes of gods, or places where Earth's inner spirit revealed itself. These interpretations were not born from ignorance, but from deep observation of nature's power. In ancient Greece, Mount Etna was believed to be the forge of Hephaestus, the god of fire and craftsmanship. The sounds and glow of eruptions were imagined as divine labor taking place beneath the mountain. In Hawaii, volcanoes are associated with Pele, a goddess whose emotions shaped the land through lava flows. These stories helped communities explain unpredictable forces and taught respect for the land. They also guided where people built homes, planted crops, and traveled. Mythology became an early form of environmental awareness. As civilizations advanced, so did understanding. Roman scholars recorded eruptions in careful detail. The eruption of Mount Vesuvius in 79 CE, which buried Pompeii and Herculaneum, became one of the most studied volcanic events in history. Preserved ash captured daily life in extraordinary detail, offering insights into Roman culture, architecture, and economy. This tragedy also transforms scientific observation. Pliny the Younger's eyewitness account laid the foundation for volcanology as a discipline. His calm descriptions remind us that even in moments of danger, careful observation can preserve knowledge for future generations. Throughout history, people continued to live near volcanoes, despite the risks. The reason is simple and enduring. Volcanic regions offer fertile soil, abundant water, and access to trade routes. These benefits often outweigh the dangers in the long term. Cities like Naples, Quito, and Tokyo exist within reach of active volcanic zones. Over time, societies developed building techniques, evacuation plans, and monitoring systems to coexist with geological forces. Modern volcanology blends tradition with advanced technology. Scientists use seismographs, satellite imagery, gas sensors, and thermal cameras to understand what is happening beneath the surface. These tools help predict eruptions and reduce loss of life. While predictions are not perfect, early warning systems save thousands of lives each year. This quiet success rarely makes headlines, but it represents a powerful collaboration between science, technology, and community preparedness. Volcano tourism has also become an important part of global travel and local economies. People visit places like Iceland, Hawaii, and Italy to witness volcanic landscapes shaped by fire and time. These destinations blend natural wonder with education, culture, and sustainable tourism. Walking across hardened lava fields or watching steam rise from geothermal vents creates a sense of humility. It reminds us that Earth existed long before us and will continue long after. Volcanoes have also influenced art, literature, and philosophy. Painters captured dramatic eruptions. Writers used volcanoes as symbols of suppressed emotion, transformation, or renewal. Musicians and filmmakers continue to draw inspiration from these powerful forms. Even in science fiction, volcanoes appear as markers of alien worlds or dramatic turning points. Their presence signals energy, danger, and creation all at once. On a deeper level, volcanoes invite reflection. They show how destruction and creation are not opposites, but partners in Earth's story. Lava destroys forests, yet creates land. Ash darkens skies, yet enriches soil. Heat melts rock, yet builds mountains. This cycle mirrors many aspects of life itself. Change can be unsettling, but it often carries the seeds of renewal. As you rest now, let the idea of a quiet volcano settle in your mind. Not erupting, not threatening, simply existing as part of a vast, balanced system. The ground beneath you feels steady. The air is calm. Far below, Earth's inner warmth continues its slow work, shaping continents, sustaining oceans, and supporting life. Volcanoes remind us that our planet is not static. It is alive with motion, energy, and patience. They ask us to observe rather than control, to prepare rather than fear, and to respect forces larger than ourselves. As this journey gently comes to a close, allow your thoughts to drift like ash settling softly after an eruption. Everything becomes quiet again. Thank you for sharing this time of calm, learning, and reflection. May the rest of your night be peaceful, steady, and warm, like the quiet glow beneath Earth's surface.